Hey everybody, today I'm going to show you a couple of different ways to compute Fibonacci sequence. This is a follow-up on an earlier video that I'll link to in the description. In the earlier video, I basically talked a little bit about how recursive solutions to the Fibonacci sequence can be generalized by basically using the notion that anytime you're doing like a two-way recursion, you have certain base cases. So the Fibonacci number, Fibonacci function applied to 0 returns 0, applied to 1 returns 1. And then for larger values of n, you have a way to split the problem into computing smaller values of the Fibonacci sequence. And then there's a combined step. And the combined step here is just literally doing arithmetic addition. And then we're going to use this recurse library that I wrote to call different versions of recursion. So the first version that we're going to test out is a real simple interpretation of recursion. Basically, kind of reading backwards, we're going to return f of n, where f is this little inner function that just says if the value passed in is already in the base cases, then just return whatever the base cases say it should be. So like in the Fibonacci example, if we were to pass in 0, we would just return 0. If we were to pass in 1, we would just return 1. But for any larger number, you split up, you call the split function to get the a and d, and then you combine the results recursively of f of a and f of b. And I'm going to demonstrate to you that this does indeed work. So here it is, computing the Fibonacci numbers. And you notice that it starts to slow down really quickly. Right now we're at the 32nd Fibonacci number, which is only 3 million something. And it's trying to compute the subsequent values. Even those numbers are relatively small by computing standards. What's happening under the covers is that you're literally like computing several million additions. Because the way that the recursion works, it's computing the same values over and over again. So I mentioned in the earlier video that there's a pretty simple solution to that, which is to use memoization, which is just kind of like another way of saying use a cache. So in this memoized version, basically I have a cache. And when I call f of I, first of all, if the I pass in is in the base cases, I just immediately short circuit that, just like the simple does. But if I is in the cache, I also return the cached value. And that seems like it wouldn't be a huge thing, but what's happening is it's not only making this particular invocation of the function faster, it's preventing you from doing all the recursive steps below. And you'll see that this leads to an enormous speed up, literally an exponential speed up. Now, if the number's not in the cache, sometimes you have to compute the first time you encounter a value of I, you do need to compute its value. So then what we do is we say that the result is combining f of a and f of b. And again, that's just the same thing we did up here with the simple implementation. But now we put the result in the cache. So if I come back here and run it with the memoized version, you'll see that it computes the first 996 values of the Fibonacci function extremely quickly. And in fact, it computes, by the time you get up to this Fibonacci sequence value, it's a huge number. It's like a really huge number. It's like probably more atoms than there are in the universe, or whatever hyperbole you want to use. But this function does fail due to a maximum recursion depth exceeded. And there are simple ways to work around that, but I'm going to show you a more spicy version. And by the way, this video is not a how-to on how to write a simple Fibonacci function. It's more of a exploration of just like some weird concepts. By the way, I forgot to mention earlier that there is like a very sane way to write a Fibonacci function. Um, Here I haven't really extracted it as a function, but if you want to build up Fibonacci numbers in the most efficient manner, you can just create a dictionary, populate the first two items with the base cases, just iterate over the range, and then each time you just iteratively make the next Fibonacci number equal to the prior two Fibonacci numbers. And we actually use this in the program, this iterative technique, to validate the recursive technique. So you can see here, after we've computed it in the iterative fashion, we compute it in the recursive fashion, and then we assert that the recursive value is the same as the one that we computed iteratively, and then we do some printing. So hopefully that's straightforward. But now what we're going to do is we're going to go to this kind of spicy version of doing Fibonacci recursively. And before I forget, I'm going to call recurse.spicy here. And then over here, I'm going to scroll down a little bit so you can see everything. Actually, let me do this just to remove some noise. So what I have here at line 27 at the top here is a generic implementation of a breadth first search. And you'll notice that there's nothing in this implementation that implies any notion of Fibonacci numbers for sure, nor does it imply any notion even of recursion. And the way the breadth first search works, most of the time when you see a breadth first search, when you're learning like how to do whiteboard interviews or you're taking a algorithms class, you'll see you have this notion of a queue. And here I call it an inbox because I'm not exactly implementing a queue, but basically I put the top thing at the top of the search tree into my inbox, and then I keep iterating a loop. And while I still have things in my inbox, I am going to get all the children of the objects in the inbox. And if any of those children are not already in the results, then I append them to the results, and then I also add them to the new inbox. And then at the end of this little inner loop here, I make the inbox be the new inbox. So I don't want to go into too much depth, no pun intended, too much depth or breadth on how the breadth first search works, but it is just a generic breadth first search. And then we get to this spicy function that does a generic notion of recursion, but it doesn't actually use recursion. It just accepts the contract, I guess, for lack of a better word, that the recursive function wants you to evaluate. So again, spicy itself doesn't say anything about Fibonacci numbers. If you were to read this code, you would have no idea really what it's computing. But when we call spicy over here from recurse_fib, we are telling spicy the structure of the recursive relationship. So we are telling spicy what our base cases are, how to split the problem into smaller problems, and then how to combine results from invoking a function or from evaluating for smaller values. So the way that spicy works, first of all, it does just, if n is in the base cases, it just immediately short circuits it because it gets complicated if you try to use this for the base cases, and it's easiest just to dismiss the base cases right away. But if you have a value of n, which in the case of recurse_fib is greater than or equal to 2, by the way, I'm assuming here that we're dealing with that n is an integer. I don't assert that explicitly, but we're assuming our recursive relationship basically is working over the set of integers, and like Fibonacci is saying that the value of n is actually equal to the sum of these two smaller values. But anyway, I have to make this little get children function that basically returns the values from splitting up I that are not in the base cases. So like if I'm trying to get the children for 4, the values would be 3 and 2. If I were trying to get the children for 17, the values would be 16 and 15 returned by get children. However, if I passed in I equals 2, normally you would think of the children as being 1 and 0, but I want to short circuit the base cases, so I'm not going to include those in the result of my breadth first search. And then down here, I want to start building up the values, so I'm going to be computing all of these small values up to the largest value, and I do need to start with the base cases, and that'll be clear in a second. But I basically have this loop where I iterate over I for this sorted list of the result of calling this breadth first search function using our incoming value of n and our get children here that I just described. And then I assert that I is not in values, because if the breadth first search worked properly, it would have never allowed duplicate values. And that assertion is basically just asserting that this line up here did what I intended. But at any rate, after that, it's like really simple, straightforward application of the recursive relationship. So I split I into the values A and B, and then I combine them. And again, here, this is not recursive. This is just literally using the values that had already been populated into my array. So in a sense, what I'm reinventing here is the actual sane way to do Fibonacci, which is that you just like create a little dictionary and you kind of iterate over the range and you keep combining values. You start with the small values, combine them into bigger values instead of doing it kind of upside down, which leads to the performance problems that you saw in the original example. But I think the next thing to do now is run it. So let's see if it works. And it does. So I'm calculating just the first 5,000 Fibonacci numbers. You can see that this these numbers get really big really quickly. Because it is an exponential function. For really large numbers, basically every Fibonacci number is the closest integer to some power of the golden ratio divided by the square root of 5. And it's a little out of the scope of the video to explain it, but you can clearly see it's an exponentially growing function. So I was able to calculate the Fibonacci value of 5,000. I didn't run into the maximum recursion depth because, as I said, Spicy itself, even though it's being passed in with this notion of what the recursive relationship is, it's not doing it recursively. So I think I'll stop there. I hope you guys found this interesting. As always, put something in the comments if you would like, and like and subscribe. Thanks, guys.